So today we are talking feature selection in this talk. Feature selection is a topic that's been, I think, pretty near and dear to me for a little bit of time. This research that I'm presenting was as much for the benefit of the community, it's for myself as well, because I wanted to kind of understand when doing the end-to-end machine learning modeling process, what types of approaches may work better than others. So that's what we're going to talk about today. First, though, I want to tell everyone a little bit about where I work. So I work at Southeast Toyota Finance, which Southeast Toyota Finance is one of the three primary business units for JM Family Enterprises, which our three lines are Southeast Toyota, which we are the world's largest independent distributor of Toyota. We cover the states of Florida, Georgia, Alabama, North Carolina, and South Carolina. And we are just an exceptional, great company to work for. I mean, I kind of pinch myself every single day I go to work. JM Family is the 17th best company to work for, ranked by Fortune magazine. We've been listed in Fortune magazine's top 100 employers to work for consecutively for the last 21 years. And the people there are outstanding. So if you're interested in learning more about opportunities with Southeast Toyota Finance and JM Family Enterprises, definitely encourage you to check our careers page. We're like a super awesome place to work. So let's talk feature selection. One of the articles that really, or I should say papers that actually kind of first got my insight percolated on feature selection was Scott Lundberg, who's the author of the SHAP library, which uses the tree SHAP implementation. He talks about the inconsistencies of other feature attribution techniques, one of which is gain, which is the default measure in XGBoost. And for most of the work that he presented, it was around the purpose of model interpretability, being able to interpret models at a global and local scale. But I also was interested in, if gain is inconsistent, then perhaps there's a better way we can do feature selection than solely on using gain. So I went and grabbed data from the Lending Club data set. It was a 2-year data set from 2012 and 2013. And the Lending Club's a very interesting data set for me, also because being in Southeast Toyota Finance, I work for a finance company. Well, this is a finance company as well. And it's very good data on labeled loan outcomes of payment behaviors of consumers. So the data set was, in essence, about 190,000 rows, 188,000 loans there were in total. 158,507 were fully paid, 29,000 were charged off. So there was some class imbalance, about 15% was the minority class. So that's something I can kind of touch on a little bit later too. So in terms of splitting the data set, I created 4 splits of the data. Split the data into a training, validation, test, and out-of-sample test set. So the out-of-sample test set was for December 2013. All the other months were either in the training, validation, or test set. I used a 40K-fold cross-validation with 4 seed values to just be as an extra added step to ensure the model generalizes. I also use that as well to just optimize the tree count as well. So in essence, I grabbed the best tree count at each of the different folds, calculated the average for all 40, and then calculated the average of the 4 averages to identify the best tree count. And that was after hyperparameter optimization with H2O's AutoML, which I can get to in a minute. So the final model was trained on the training, validation, and test sets with model metrics measured on the out-of-sample test set. So in terms of the feature engineering and resampling that went on, first I actually tested not doing any type of oversampling or undersampling. Again, the minority class represented 15.7% of the data. So generally, usually I find oversampling and undersampling helps with 10% or less, but in this case, actually I found lift with oversampling and undersampling. And that would be only in the training set of the data, and that was essentially the approach that I held constant for all 5 experiments. Categorical data was both label encoded and target encoded. So essentially, target encoding is going to provide representation of the mean value, which in this case, 0 being paid as agreed, 1 is being charged off. That mean representation for each of the values in the categorical feature. Weighted evidence transformations were calculated on all features. So weighted evidence is a common practice for finance companies for modeling data. It's something that we've done for a long time, which essentially I took the natural log of the percent of event rate over percent of non-event rate. So in that case, doing that, it's a binning algorithm. And when you do weighted evidence binning, essentially you're going to create multiple bins, and if a value has a positive value, that would then indicate that there is a greater representation of the default class in that bin. If it's negative, there would be a greater representation of the non-default class. So let's talk kind of the process flow for how feature engineering worked here. So first I took the categorical features and I duplicated them. So all the categorical features, I created a duplicate column, and then I went ahead and label encoded that duplicate column. The unduplicated categorical features, I target encoded. Next, I then duplicated all the features and essentially calculated the weight of evidence transformation for those duplicated features as well, and dropped any features with constant value. The black box represents experiment number 5. So I'm going to get to the 5 experiments here in a second. So this is actually a technique that I've thought about for some time as well, and have seen success with, where when you're having a training, validation, and test set, your training set should be used to train the entire model. Your validation set should be used for hyperparameter optimization and feature selection. Your test set should never be touched except for evaluating model performance. So with that thought, one of the things that I was thinking about is it's always important to make sure your model is going to generalize to unseen data. And could we help avoid any additional data leakage if instead of my initial feature selection process of essentially creating a model off the training set and measuring model performance in the validation set, what if instead of doing that, I split the validation set into essentially 80% of the validation set represents a training subset and 20% of that validation set represents a test subset, and then do backwards feature selection only on that subset of the validation set. Later at the end of the experiment, I then switched when I went to H2O's AutoML to train on the very final model runs of the entire training set and measure performance in the validation set. So it's a little bit of a wrinkle, but actually when I show you results, it actually worked best. So we'll get to that in a minute. The FeatX package is a package that is also a very interesting package that has been talked about for use in feature selection. In this set of experiments, FeatX didn't add lift, but I think it still is something that is worthwhile of trying, and I think it may be just a function of this data set. So basically what FeatX is going to do is it's going to bin on a univariate basis every single feature into fixed member bins, and it's going to then assign the mean value of the target variable for each of those bins for that given feature and plot it. And it'll do that on the training set and then on the validation set. And then it'll measure the Pearson correlation between those two splits. So in essence, if you have a low correlation, let's say a correlation like maybe 0.3, that means you have really noisy data. The trend line of the training set does not match the trend line of the validation set. And the premise of this package is that if a feature could still show high feature importance, such as gains, the gain measure, but even though gain importance is large, the feature is still noisy, it won't generalize to new data, and actually on an out-of-sample test set could provide adverse performance. So in this instance, it didn't add lift, but I still am planning on using it pretty much every time I'm doing feature selection and having that as one of the steps that I'm going to be doing. So then after I used the FeatX package, then I went ahead and fit the initial model, gain feature importance values for all the features using gain. And you might be wondering, okay, so I talked about gain being not always consistent. Why am I still using it? And gain has one good, very nice quality, is that it's not slow. So I'm going to talk a little bit about using Shapley values, as I mentioned from Scott Lumberg, and Shapley values are much more computationally intensive. So if you are fitting hundreds of models in a feature selection process, if you were to do all of those model fits using SHAP, it probably would be computationally intensive, would take a very long period of time. So when I actually built out, this is in the black boxes here being experiment 5, which I'll get to in a second. When I did experiment 5, I started with gain, but I then did one extra thing, and I used the XGB-FIR package. So XGB-FIR is the R port of a package which identifies all of the relevant two-way and three-way interactions of features in an XGBoost model. So why would I want to do that? Well, it's also essentially going to be computationally impossible to brute force calculate all of the two-way and three-way combinations on, say, 100 or 150 features. You start getting into thousands of features very quickly, and it's going to take the code a very long period of time. So if you use XGB-FIR, it'll actually tell you what are the top 100 two-way combinations and what are the top 100 three-way combinations of your features, and do the mathematical calculations between those two-way and three-way interactions and put them into your feature set for feature selection. So that is one step that I did, and then I did stepwise backwards feature selection with different approaches. But the first part of that stepwise backwards feature selection, I always used the gain measure. I then reviewed MLflow, which I know there's been some talk about MLflow. I love MLflow. Like, I think it's the best library. It's made my life so much easier. There's other libraries that I think are coming into the community right now, but whatever you use, if you're using, actually just saw that SageMaker just introduced a new library for experiments. Use something like that. Don't use Excel spreadsheets. So, and then after reviewing MLflow plots, I then figured out, okay, what is the optimal set of features that I should be using? And then I did something different. So I mentioned I found the relevant two-way and three-way interactions. And in this data set, I used the two-way interactions that were relevant. And then I actually parsed those out. So let's say, and you'll see my final model run was at 61 features. Those 61 features actually reduced down to 20 when I parsed them out, because it might be a two-way interaction of feature A and feature B, and then the next feature may be feature A and feature C. Well, then when parsing it out, actually ended up being a reduction in total set of features. So I parsed that out and then passed those final set of features into the final feature selection process, which was either using gain on a stepwise backwards process with H2O's AutoML, or using Shapley values and a final backwards stepwise process using H2O AutoML for hyperparameter optimization. Kept the same runtime sets for when I did AutoML, so all other potential variables in the experiment were held constant. And then I should also say, before I did the final backwards stepwise process, this box right here, I eliminated the redundant features as well. So if there was a main effect feature or a transform feature, I dropped those, the one that had the lowest importance. So these are the 5 experiments that I tested. I first started with experiment number 1, which was backwards stepwise with SHAP. Next, I did backwards stepwise with SHAP and feat-exp. Then I did backwards stepwise with gain. Experiment 4 was just a single elimination of the same count of features with gain. And then the final step was doing backwards stepwise with SHAP, and that one I also split the validation set. So on the first experiment, when I did backwards stepwise with SHAP, and this was not splitting the validation set, what you'll see here is this plot point of highest AUC in the validation set was at 170 features. That was actually the first model fit. So what actually happened here was when I went ahead and calculated the relevant two-way interactions, which got me out to 700 features, you can see AUC is lower, and AUC never got higher. So in this instance, essentially what I did was I ended up staying with that 170 feature initial model run. When using the feat-x package to eliminate noisy features, instead of starting with 127 features, I ended up starting with 43. As 127 of the 170 features had a correlation between the training and the validation set of less than 0.75. I also tested a correlation threshold to cut off at 0.90. That was actually worse than using a correlation threshold of 0.75. So the 0.75 value is what I used for the rest of that experiment. So in terms of finding the optimal count of features backwards with SHAP, so I had that 170 feature first model run. I parsed out, and so basically, what I ended up doing on that experiment was actually just then backward stepwise feature selection. And this is the type of scatter plot that I'll usually see when I'm doing backward stepwise feature selection. It's kind of like a reverse hockey stick where it's going to be pretty constant and then it's going to start dropping. What I like to do is choose the model that's going to be most parsimonious and have the fewest amount of features, which provides benefits for interpretability and also computation and inference. So in this instance, I actually chose the model at 17 features. Perhaps could have also chose the model at 24 features, but I went with 17. And from that experiment run, I then held that constant for all 5 other experiments. So all the other experiments that I tested, I always used 17 features just to make sure I had an apples-to-apples comparisons between the different experiments. So when splitting the validation set, there's kind of a different look here. And so this was the first model fit at 170, and you can see then when I did the two-way interactions, we got an AUC down here right at about 0.585, and then I did backward stepwise feature selection all the way down to 1 feature. And sometimes there's jumps because in this instance, between those 2 runs, they all had a feature importance of 0, so they all got dropped. So I'm essentially iteratively going through and eliminating the feature with the minimum feature importance and continuing that through with the Guinea importance measure, gain. And so as you can see here, right at 61 features, that actually was the highest AUC. And then the next step of this experiment was then to actually parse out those 61 two-way interacted features all into single standalone features, which actually got us down to about 20 features. The other thing that I should say too that reduced us down to 20 features was the elimination of when there was a main effect feature and a transform feature. I eliminated the feature that had the lower feature importance. So let's say if the label encoded feature had less feature importance than the main effect feature, then I kept the main effect feature. So then another thing I want to do, and I know this is going to be a little bit hard to read here, is I created a linear model for these scatter plots to see. Let me come back to this plot here. So you can kind of see here, like you could kind of fit a linear model to that data. So I fit a linear model to those AUC values, essentially with the different feature attribution methods that I'm testing here of SHAP and splitting the validation set, and that had R squared of 0.793. SHAP and splitting the validation set with a p-value of less than 0.0001. And then if I just did SHAP alone and not splitting the validation set, the R squared was a little bit less at 0.722. And the p-value is still good, less than 0.0001. And then when I used gain, the R squared was even lower at 0.535. Those values were, when fitting a linear regression for the model metrics on AUC on the validation set for the runs between 6 and 20 features. And I chose that because 20 features was the first run that I had when I split the validation set. So I mentioned I had 61 features. I parsed out the interactions, and I also eliminated redundant features between transformations and main effects, which got me down to 20 features. So that's essentially why I set that point. And 6 features was essentially used at the low point, because after I had less than 6 features, the model really started to degrade in performance. So that I think is a good measure that of these different types of approaches, that on this data set, that SHAP and splitting the validation set was going to get me predictable results as I'm going through the feature selection process in a stepwise manner. So kind of with that said, I've talked about these 5 different experiments, and I can kind of come back here again. So these were the 5 different experiments that we tested. I think what everybody probably wants to know is like, well, how did this actually work? So when looking at the results, the best experiment was when I was doing stepwise backwards feature selection, first with gain, and then finally on the last few model runs with SHAP and splitting the validation set. You can see the AUC was at 0.674, average precision score was at the highest at 0.251, and the log loss was 0.468. You might think AUC of 0.674, that's not really that great. Well, it depends. I think that always depends on what the problem is you're trying to solve. So in this instance, again, we're trying to predict people if they would default or not on their loans. Being an imbalanced data set, it's not something that happens that often. There's a lot of reasons why people can default that aren't within the data. Perhaps when their loan originated, they had this fantastic job, and then 3 months later, something happened and they lost their job. And maybe that's why they couldn't pay back their loan. So some of that is always going to be dependent on the problem that you're trying to solve, and that's your model's only going to be as good as your data, and there's aspects that you might not have of predictors that might not be in the data set. So looking at some of the other approaches, so experiment 1 was the backward stepwise with SHAP at 0.650. The single step elimination of features with gain, which is an approach that I think is quite common, is I actually had ranking 3rd here at AUC of 0.647. Backward stepwise with SHAP and feat exp was at 0.641, and backward stepwise with gain was at 0.639. So you can see here, in terms of a percentage difference of what do those model runs represent, you can see AUC was just over 3% higher between experiment 5 and experiment 1, and log loss were lower, better, 10% improvement. So that suggests to me that this approach of using gain in conjunction with Shapley values definitely provides a good opportunity to enhance some of our feature selection approaches or feature selection methods that we may employ to get better model results. And I think those results also show here that there's a fair amount of variability in these results here. So the feature selection technique that you employ definitely matters and can have a big impact on how well your model performs. So in conclusion, there's a couple things that I think I want to talk about. First, backward stepwise with SHAP, obviously I mentioned was best. Results may vary on your data set. So that's, I think, a very important point to mention. So if this approach works well in this data set, maybe on a different data set, maybe another approach may work better, but I think it's worthwhile to consider different types of feature selection techniques in your code base and test multiple different approaches. I would definitely recommend using an experiment tracking platform such as MLflow for A/B testing. MLflow is it's great. It's super easy. It's something that you can use for literally. I've logged thousands of experiment runs into MLflow, and this whole ability of being able to come back after you're done and just having everything logged and being able to look at these types of scatter plots when you have hundreds or even sometimes thousands of model runs to say, okay, that's the best one. I really like this one right here. That is really nice. So I would, if nothing else, I would definitely have an experiment tracking platform that you have in your workflow. And then on this fourth to last conclusion, gain provided a performance benefit over SHAP. Using interactions with gain may add lift. So that's something that I think interactions is a common approach that we use as data scientists for feature engineering, but it may also be worthwhile to consider that if we know that gain is not always consistent at the way it represents feature importance values, and one of the things to kind of take a step back here that Scott Lumberg mentioned was that what he found was with gain is that the features that were actually lower in the tree had higher importance, which gain essentially provides a measure of the log loss lift on average that standalone feature contributes in the model, where if that feature is removed, what's that difference in that log loss? Gain, he actually found that features lower in the tree provided a higher gain value than features higher in the tree, which doesn't really make sense. Because normally when you're thinking about a decision tree, the top of the tree is going to be the feature that has the most importance in the model. So that's something that I think is really important to kind of just think through, is that, okay, yeah, gain can give us a measure of importance on a global scale of how important a feature is, but there are some limitations with it. And if you do something like what I did, where I created basically interactions of features, that interaction process, it's likely that even though it's not always consistent, it's likely that in one of those interactions, an important feature won't be omitted, and it'll be kept in that interaction. And then later on, then in the feature selection flow, I can then do backward stepwise with SHAP, parse out those interactions, do backward stepwise on SHAP. I'm only fitting maybe 5 or 6 models. It's not like I'm fitting hundreds of models. And then it may take a little longer computationally, but if I develop my code in that type of process, it doesn't become a computational problem where it's taking days or weeks to complete. And lastly, I mentioned Scott Lumberg used SHAP for interpretability, and like for me, that's something that has been really a great package. I really enjoy using SHAP for model interpretability and communicating internally and externally the benefits of the package, and how it's really something that kind of dispels the notion that these are black box models, because they're absolutely not. They're definitely interpretable. So I would say with that, I mean, that probably concludes my presentation. We can open up to Q&A.
So in your results, you were bouncing between, it looked like about 55% AUC to 62% AUC. Have you done this on a, I don't want to call it a like not toy data set? Like, have you done this for real? And have you gotten similar results? Because I'm not really sure how to translate a 7% jump in AUC in that range as to whether or not it suddenly makes it useful. Like in my problems, a 62% AUC is like, you still got it. You still have garbage. Yeah. So like how does this work for a larger data set that's more relevant to what you're doing?
Yeah, great question. So I have used this type of approach before. I can't get into too much detail in the projects and things that I've used it before, but it definitely has given me lift in doing this type of work. And I would say don't get too fixated on the number. Get fixated probably more on these percentage changes. So like for me, if I can get another 3 or 4% or 5% in my challenger model to my champion model, absolutely worth it. So yeah, I think it's definitely something worthwhile to take a look at.
What was the inspiration to do the comparison for the different models for you, like using?
It was mainly Scott Lumberg wrote a Medium article introducing the tree SHAP package, and he talked quite at length. So I'd encourage you to Google it. It's still on there. It's a great read. And he compared at length the different types of feature attribution methods that are used and the benefits of how SHAP, since it uses Shapley values, and it provides essentially a consistently accurate, he describes it, method for understanding global feature importance. And from his angle, he was kind of taking it as, well, we're trying to interpret a model to understand what are the most important features, Well, feature importance is also a process that's often used for feature selection. So for me, when I'm looking at that article, I'm thinking, okay, if this is really not that consistent, well, then there's probably some improvements that can be made in the feature selection workflow. And that kind of was like my inspiration for going after it.
All right. Thanks again to Ben Fowler for that talk, evaluation of a traditional and novel feature selection approaches.